Okay, thank you. Good morning, everybody, for attending in person to this Friday talk. Lately, it's difficult to have a full audience because everybody's watching online or just Googling YouTube and watching the presentation afterwards. Here we have the honor to see the presentation of Derek Sawyer. Mm-hmm. He's currently associate professor at the School of Earth Science at the Ohio State University in Columbus, Ohio, in the United States. He's the PI of the Marine Geology and Geohazards Lab there, and studies earth dynamics and surface through experimental field and numerical studies of natural geohazards. That's one of the topics or the line of research of our institute, impacts of geohazards. So we have the honor to learn a little bit about this today. He got his PhD at the University of Texas in Austin, and then he worked for 2 years at ExxonMobil Exploration Company for global deep water exploration and development projects. So he has this part of working with the industry that's also interesting. Now he works closely with the International Ocean Discovery Program, the IODP, formerly known as International Ocean Drilling Program. It's those vessels that drill deep into the ocean and learn about the properties of the sediment recovered on the drilling. And he worked mostly lately in the Gulf of Mexico deep water gas hydrates expedition. He was a visiting scientist at the ICM during 1 year sabbatical in 2021, 2022, working closely with Roger Joles and Xavi Garcia and Claudio Loiacono. And this collaboration resulted in a paper published in 2023 in Journals Geology. And now Roger has suggested his name as a potential candidate for the ICREA positions because he wants to eventually settle here and continue his career here at the ICM. So, and this is one of the presentations that from the strategic committee of the ICM asked to the people that has some interest in being employed here at the ICM. So like a presentation, personal presentation and scientific presentation to all the members of the ICM so we can know him better. Okay.
Thank you, Peter.
You're welcome. The floor is yours.
Okay, great. Okay, sound check. Oh, is that good? Okay, great. Yes, thanks very much, Peter. Thanks everyone for the opportunity and for coming here, and for those who are online, of course. Yes, as Peter said, I'm currently at Ohio State. I've been there 10 years now, and have been working on a variety of projects around the world in the broad theme of underwater or natural geohazards that exist under the oceans, and exploring those systems in a number of ways, directly accessing them with drill ships. The picture here, anybody know that this ship? Not the Chikyu, the U.S. one. The one that's being retired, sadly. The Joides, yes. The Joides Resolution, exactly. I first met Roger Urgelis on this ship. I don't know, must have been 20 years ago. I was a graduate student at the time, and Roger and I met for the first time in Mobile, Alabama, I think, and then spent 8 weeks on that ship in the Gulf of Mexico. So I was thinking back to my original connections to ICM, perhaps go back as far as 20 or so years ago. That was way back in 2005. Since then, so as I mentioned, I've been sort of involved in a variety of lines of research throughout my career. So I'm happy to sort of give you a brief summary of the things I've been working on, most recently, of course, to give you a sense of what I do and the things that I'm studying, not just myself, but my research team, groups of students and postdocs and collaborators across the globe. I want to start a little bit by just thinking about the news that's right now, as we're sitting here. I'm sure many of you are aware of what's going on in Santorini. There's a state of emergency declared for the island in response to the swarm, thousands of individual earthquake events that have been occurring. These are just some of the largest, but in terms of total number of events, there are, in fact, thousands. So it's a very dicey situation at the moment. It's not clear what may happen, perhaps nothing, hopefully, but in people's minds are back 1956 when a 7.5 magnitude earthquake hit and triggered a tsunami, which triggered a lot of damage and also deaths. So this is another example of the constant reminder we live on a dynamic planet, and some locations are constantly under risk or vulnerability of some of the systems that we as natural scientists are trying to understand. So myself as a scientist, I looked for evidence of things like earthquakes, earthquake-triggered events, as they are recorded in sedimentary deposits, as they make their way out to the bottoms of the oceans. And we can understand those deposits, we can understand their frequency, we can understand their periodicity, and hopefully their origin, where they came from. But that's a very tricky endeavor, so it's not quite as simple, but that is a lot of what we try to do when we're trying to study these natural phenomena, is try to understand where they occur, why they occur, how frequently, with the hope of perhaps increasing our resilience as human society against these. Okay, so just some pictures of my research group. I'll study, or not study, but present a little bit about these. I'll focus today on volcanoes, earthquakes, and underwater landslides today. Active projects going on right now. There's, like many of us, we have a lot going on. I can, projects on active margins, passive margins. Here's Mediterranean. I'll start with this project here, and then Turkey, and then Japan, and some earthquake studies. So a lot of active projects going along around the world. Okay, yeah, I want to start with the Mediterranean, or in fact the Tyrrhenian Sea, as this is the project I worked on during my sabbatical when I was here at the Institute, working with Roger and Xavi Garcia and Claudio. We working on a project that was originally a discovery of a series of what we call megabeds. Megabeds just means exceptionally thick, also wide, basically large volumes of individual sedimentary deposits that are making their way out to sedimentary basins. They're quite large because we normally don't see them as thick. And so we've been seeing these for the last couple of decades around the planet. We don't really know exactly their origin, but we suspect they're probably tied to big energetic events that are releasing or capable of releasing that much sediment all at once. So this is an interesting view. You're looking at a perspective view of the Marsilli Basin. We're here in this yellow shaded area just northwest of Italy. And in the center of the basin is a large active seamount. This is the Marsilli Seamount. It is an active volcano. It's among the largest active volcanoes in Europe. And in the basin floor, especially in this area, we're looking at a profile down here through the deposits of the floor of that basin. And when I came here and sat down in Roger's office, he showed me this line, and we started asking questions. Well, what are these acoustically transparent, these more clear beds that are thick, they're expansive? Let's study these. And so we launched into this project that culminated in a nice study. So I'll just walk you through some of the highlights of that. Here's another view of the setting. Again, the Marsilli Seamount here, and most of our study area is off here. And when we were starting this, we thought, well, maybe those big beds are probably sourced from this active seamount, this active Marsilli Seamount. It's right nearby, of course. And there were papers that have been published recently at the time that were suggesting that this is a source of, basically flank collapse events that would then feed into or fill in the low parts of the basins. So that was sort of a starting hypothesis. But it turns out, when you map these things around, their distribution and the way they thin and thicken do not support the suggestion that they're sourced from the actual seamount. Let me get into some of the more details and come back to that here a little bit later. In 2015, as part of the Chianti cruise, leg 4, I believe, of the Chianti cruise, Roger was part of that, collected a series of high-resolution geophysical profiles, one of which you saw there, and a variety of gravity cores. So the stars are the cores that they collected in 2015. But really the most important one is this site here. Site 650 of the ocean drilling program, way back in 1986, drilled that position, kind of ideally situated for our project studying megabeds. At their time, they did not have high-resolution geophysics. They were unaware that these megabeds existed. And so one of the first things we did was just tie or link the geophysical data that you see here to ODP site 650, the actual sediment properties, so we can actually match what's actually there with our geophysical facies. The short story is, this is the sort of the raw data. There's at least 4 megabeds. We're seeing the first 3 here. There's one that's just in there. It looks tiny there. It's pinching out in this location, but it gets thicker in other locations off the line. But there's a sequence of at least 4 of these megabeds, and in the time frame we're looking at, this is within the last 60,000 years. So there's some repetition going on in this basin of these large events, megabeds that are happening. And in between the megabeds, you can see there's a period of quiescence or normal background sedimentation. And today, the modern seafloor, we've been existing or experiencing a period of non-megabed deposition for some number of years. So, understanding the origin of these megabeds is important to understand the future, perhaps risk of another event occurring in the future. These events are kind of fun when you start mapping their details. They look simple at the start because they're kind of transparent facies, but when you start mapping the bottom especially and some of the internal features, it turns out you can see evidence for really rapid emplacement that induces some fluid injections. Basically, when you have a big pulse of sediment, the sediment underneath that's feeling that load responds by jostling and deforming and sometimes dewatering itself. And so you get these classic fluid venting features. You get these tiny little injectites at the top of the bed or from the top of the bed. And even there's evidence that the bottom of the bed is so energetic that it's actually scouring out the seafloor itself. So this is evidence of, again, single events coming in pretty energetically into here, the Marsili Basin. They don't really exist unless we're in the very lowest parts of the Marsili Basin. Okay, so this is a seismic profile in this location, which is basically a subtle topographic high just north of the Marsili Seamount, and this is a good line to see where the megabeds are not. They are absent from this local topographic high, and they only exist down in the deeper parts of this basin. So they travel along the bottom and then they spill out as far as they can, but they are relatively contained or confined within the available space at the floor of the basin. This is a map of one of the megabeds just to show you the distribution. It's a little bit hard to see, but if you can tell, this feature is the Marsili Seamount itself, and so just the colored variations here are thickness variations of 1 megabed, and it shows us the variation. And what it actually gives us insights into is where it perhaps came from. You can see it gets thickest down here and thins out to the north and to the south and also to the sides as we get closer to the boundaries of the basin walls. There are a lot of potential sources for these. We're trying to understand where it came from, and in reality that's pretty complicated because of all the pathways possible. The Marsili Basin is here. Here's the seamount. Here's Site 650. All of the arrows here are showing you all of the potential pathways that sediments can get out and probably have over various years. Now, the megabeds themselves is what we're really interested in, and so we have to consider these possibilities. It's probably harder to come in from the west, and it's probably harder to come in from the east because of the seamount itself is kind of in the way to match that map I just showed you of the distribution of the megabeds. But there is a sediment feeder system off to the east related to the Stromboli canyon and fan system. Just for the sake of brevity in a talk like this, after we spent a lot of time looking at a lot of the data and possibilities, it looks like the timing of events and the megabeds themselves, and also the chemistry, which I won't talk a lot about today, is consistent with these megabeds being sourced from the Campanian province of Italy and the Phlegrean fields. And there's a very significant eruption, a super eruption, about 39,000 years ago, the Campanian ignimbrite super eruption. And then there was a younger one, also in the same region, at about 15,000 years ago, called the Neapolitan yellow tuff. A little bit less energetic, but still categorized as a super eruption. So these are coming from, the Phlegrean fields here of Italy, and the original one, the Campanian ignimbrite, was impressively violent. Here's just a plot of the volcanic explosivity index, so just a scale system for, least to most energetic or most explosive. And the Campanian ranks as a number 7, which is among the largest that we know about on our planet. This system has been well studied, this Campanian ignimbrite, mostly on land. And so the map here on the right is showing you, oh, I lost my pointer, there we go. This map is showing you distributions of the ignimbrite itself as mapped by, basically surface geology. But, there's a lot of inference that there's a lot of marine records that perhaps has not been well confined or constrained yet. So, in fact, part of this study, we think anyway, is actually we're finding remnants of at least part of the Campanian ignimbrite itself in the Marsilli Basin. And so, yeah, we published that paper as sort of hey, we found these megabeds. We think they're sourced from some of these super eruptions from the Campanian ignimbrite or the Campanian province, but we need to study these more. And so that sort of laid the groundwork for some further work that have been continuing on in the years since. And so just this past summer, a student of mine, Faye Higgins, pictured here, she is working on her master's degree with me back at Ohio State, but she got really interested in this project when I was describing this to her. And so we spent last summer redescribing the original cores from Site 650 that were collected in, like I said, the late 80s that have been sitting in storage in Bremen, Germany since then. So we reopened them. It was quite exciting to look at them. And we also did a few things. Behind Faye here is the XRF scanning facility. Again, this is in Bremen. And so we did some detailed scanning of XRF elemental distribution so we can actually get the elemental breakdown at very high resolution, every centimeter, down core, with the hope of maybe we can fingerprint chemically where some of these megabeds and other events are coming from. In addition, Faye was doing a detailed redescription of the original cores because the original sedimentology team didn't know that there were geophysical things that we call megabeds now. And so we wanted to have a fresh look at the cores in light of the new evidence from those geophysical profiles showing the megabeds. So we did that, and then we moved down here to ICM. So Faye visited here for a week, and we worked together with Roger and others, and we did some numerical modeling, testing ideas related to debris flows and turbidity currents, trying to understand, is it feasible for sediment flows to get out this far into the Marsilli Basin if they do start from places like the Phlegraean fields. So ongoing studies here. She's rapidly working on some of her projects, and she's produced a number of really good products so far. This is her reimagined stratigraphy column based on our visual work, like I said, this summer. And sure enough, we do see the megabeds are popping out. The first one here is here. This is a classic megabed. What you're looking at is 9 meters of sediment, and it's coarsest at the bottom, and then it's fining upwards. That's evidence of single event that's sort of stratifying as it goes down slope, and it grades upwards into the finest stuff until you finally get mud, clay, and silt at the top as things quiet down. Then, as time goes on, we get another pulse of sediment, a megabed, but it looks very differently than the one below it. It has characteristics of internal deformation that we don't see in the lower one, so this is acting more like what we call a slump or a debris flow, whereas the bottom one looks very much like a classic turbidite sequence. And then the youngest one is a little bit more puzzling because it's in this stratigraphy, but we don't see an obvious evidence for where the megabed is. So we're trying to refine our tops and bases as best as we can. What does help are a couple of age dates that we acquired. There are some marine shells here, fossils, that we were able to isolate when we were describing and sent those off for age dating. And basically, they support our initial ideas, or they're consistent with the timing that we thought all along, that this stratigraphy is older than 30,000 years and younger than 60,000 years. We can't really tie them. We don't have enough age dates to really pinpoint or match events to megabeds yet. And then the plots on the right are just profiles from the XRF elemental scans. And there's a lot of data here. I won't go into the details, but I just want to show you the wealth of quantifiable data that you can get from rescanning these cores. It's also a shout out to IODP and anybody who keeps cores, like the Institute here, for a long time. You never know what new data you can acquire and what new discoveries you can make. And these cores have been sitting in storage for 3+ decades. So more to the story coming about the Marsili megabeds. One of the things that is emerging that I think is kind of fun is that, yeah, as I said, each of the Marsili megabeds, even though they look quite similar in geophysical profiles, the actual core material is quite complex. And if you read the literature, this is a kind of a new thing for people who study megabeds to appreciate, because I think there's a consensus that, okay, a megabed is a simple or relatively simple turbidite. It's just exceptionally thick. That's probably true in many cases, but especially in the Marsili, I don't think that that's what we're seeing. So there's some complexity here that we didn't really understand that well. So the Marsili Basin might be a great location to really understand more of the subtleties or complexities regarding megabeds. These cartoons or illustrations are some of the detailed work that Faye's done. I told her she did an amazing job. I think you agree these are nice illustrations. but they're putting together our thoughts that we have in our heads, and they serve a great purpose when you try to explain what you're seeing in the rock record. And so what we're envisioning here is, okay, we maybe have a volcanic explosion that is happening, perhaps the Campanian Ignimbrite, for example. We know we have two canyons nearby, the Magnani and the Sorm Canyon, I believe, are right near this area, and they directly connect to the deeper parts of the Marsili Basin. So it's an obvious pathway, possibility for sediments that are getting energetically distributed or remobilized to find their ways to the canyons and get flushed down to the bases of the canyons. As they do that, maybe one canyon gets more at one time and the other canyon is maybe less full. At the same time, if canyons are allowing material to come out, they're going to run up to the sides of the seamount perhaps and get deflected and get reworked with other downgoing flows. This is just an idea, but it gives you a sense for what's possible to explain some of the complexity that we're seeing in some of these megabeds. That it's not just one single event that's nice and simple to explain. You have these individual entry points of individual flows that perhaps are offset in time by maybe days. And so in the end, when they get out to the basin, we get a very mixed signal in the end. So we'll see. We have much more to unravel on that front. Not only in the Marsili, this story is interesting because it could expand, because we see them, of course, in the Marsili I just showed you, but if you just go to the nearby Vavilov Basin, we see, again, these exact same things that we see in the Marsili megabeds. I don't know if they're correlative, but if they are, that would add a lot more volume. If they're the same, if they're coming from the same event, it would add a lot more volume to these. We've calculated the volumes that we can map in the Marsili Basin, but in fact, if some of these are correlative, then the volumes will get much larger. This project is fun because IODP just finished an expedition there less than a year ago, and so there's a lot of cores and material or sediments and data that are coming from the Vavilov that I think will hopefully be important and maybe closing that story of, are they similar or are they different in terms of the megabeds? Okay, that's the megabeds in the Marsili Basin. I want to transition gears here a little bit to think about earthquakes now. We're still going to talk about megabeds for a little bit. This is a project in Japan, in a place called the Japan Trench, and it's part of an IODP expedition 386. It's a picture of the team here. I got a chance to go out on, this is the deck of the Chikyu actually, where we were finally able to look at cores that were collected in, again, very deep basins offshore Japan. In fact, these cores, I think, set records for the drilling program in terms of water depth that was ever drilled. This is 8,000 meters plus water depth. Very, very deep sedimentary basins off of the margin of Japan. And I'll just show you. So here's the location. The expedition targeted a series of these very deep, what we call terminal basins. These are the deepest, end basins where material can get out that starts from the margin. And the hypothesis is that because we know there are mega earthquakes on a subduction zone setting such as this is a good place to go and do what's called paleoseismology, where you go into these deep basins and you try to identify earthquake-triggered deposits with which to expand the database for earthquakes from the historical or instrumental records. That's a tricky science because how do you know a bed was triggered by an earthquake? And so there's a lot of details to work out with that technique, but that's just the overall goal of the project. I just want to show you a few interesting, some plots that are coming out. This is a very new project, still rapidly moving along, but we see very similar things, even though we're in another part of the planet than what we just saw in the Marsilli. We start with the geophysics, and we see this very young, near seafloor event that's several meters thick. It sits in the bottom of the basin, it thins out to the sides. We cord right in the middle of it, as you can see with those 3 bars. And here's a picture of one part of that. And so let's start here at the bottom. Basically, we have a sharp contrast, or contact, where the base of this event is here, with a coarse, sandy, rich deposit that's only, maybe 10 or 20 centimeters thick, and then it's capped by this stuff, this grayish, tannish, brownish mud, which is most of what you see in this deposit. Most of that is the mud. And this, again, is a very classic way that megabeds are manifesting themselves in sediment or in cores. And it suggests that it was one single pulse of sediment, coarsest sediment, and then you get a thick, almost structureless mud cap at the top. And then there's other evidence, if you look in the interior of some of these beds, where you see small-scale deformation that you don't really see with your eye. This is the picture of the core, and this is the CT scan. So if you've ever worked with CT scans of cores, you probably know the value of them. You can really see things that are subtle density differences that you don't really see with your eye. But they show you, especially when you have debris flow type material. So those are characteristic. There's a lot of these in the basins. I just want to show you one to get you thinking about what earthquakes do, because we'll transition to that here in a second. One last thing that I think was fun, if you look at that same megabed and now you look at the physical properties of it, it's interesting because it's sitting there, it's a pile of sediment, but it's pretty young. And we think it's young because it's not fully dewatered yet. It's retaining a fair amount of porosity, and it's not really compacting as much as it normally would. And we can detect that based on, there's a lot of data here, I'm sorry, but basically this red line, if you can think about density, it's a lower density in most of that deposit, suggesting that it's, holding on to a lot of water. And so it hasn't had time to sit in the basin and allow compaction processes to take over. We can probably use that to our advantage. I've been thinking about maybe there's a way to have maybe a novel approach for age dating that event. If it's still in the process of dewatering, we know the process of dewatering is consolidation. It's a well understood phenomenon. It's basically diffusion of water vertically. And so we can at least start there and simplify this and think about, okay, well, what is the time-dependent consolidation going to be for materials with mostly mud? We can understand maybe the suspected permeability, which is going to control that time scale. And we know the thickness of this event. And so we should be able to constrain a little bit about how long it would take to fully diffuse the internal fluids away in order for it to be fully consolidated. So this is just a conceptual model of doing that, and you can work out, this is a very simple way to do the 1D diffusion, and it turns out for this particular event, in order for it to get fully consolidated, it would take about 700 years, all right? And the error bars are related to how well we know permeability, and so there's some error bars on this, of course, but yeah, it might take the order of, century scale for this thing to fully dewater. So what does that mean? It looks like it's still dewatering. Therefore, it's probably, of course, younger than that. Can we refine that more? Perhaps, but not at this simplified first scale. But there's hope there. There's actually some interesting, avenues for age dating or confining age limits, I suppose, on some of these events. Okay. Thinking a little bit more about earthquakes, I want to step back a little bit and just let you know some of the things I've been working on in addition to megabeds. Now, it's probably no surprise. If I say earthquakes and submarine landslides are related, you probably won't have any problem with that suggestion. And that's true. But interestingly, over the last, I would say, couple decades, as marine scientists have been looking around our planet, where we have, of course, earthquake-prone areas, looking for landslides, there seems to be this paradox where there's not as many or even as large submarine landslides where we have the most seismically active areas on our planet. On the flip side, where we have seismically quiescent areas, passive margins, we actually still find very many and sometimes very large submarine landslides. So there's this bit of a paradox of why do we see this inverse relationship where you have the most energy, but why are there fewer submarine landslides? I want to show this interesting video that is from some scuba divers that were diving in the Philippines here and happened to be diving at the time an earthquake occurred while they were diving, and they were videotaping. So this is a really rare video. I've watched this a few times. Maybe you've seen it. Hopefully I can play it. And I just want you to see what they capture in the video. So a number of things are happening, right? Pretty dramatic. In terms of the sediment, you see this cloud, this turbidity that is being caused by the shaking. You probably saw some pieces of rocks that are moving, and so, this is a pretty large earthquake, magnitude 5.9. That's energetic enough to do that type of deformation or damage or sediment mobilization. But there's a number of things that we don't see. There's no submarine landslide, at least what we can tell, and from what I can study of this event, there was not one. So not every earthquake will generate a submarine landslide because it's not large enough or it's too far away. And so if you're giving any one location, if it's on an active margin, it's probably going to experience thousands of earthquake episodes during its early burial years. That might take 10,000, 100,000 years. And so I've been working on this question of what does non-failure or what do non-failure earthquakes do? They impart energy to the seafloor sediments, but what does that do as a consequence? And does that help explain why we don't have as many earthquakes or submarine landslides on earthquake-prone margins? So I wanted to answer that question, or at least look at that question, using the global database from the 50-plus years of ocean drilling programs and its predecessors. And so all I'm doing is just archiving the available thousands of data points that have been collected over the years of what's called the undrained shear strength, the shear strength of the material. And it's a routine measurement among many that is collected on IODP cores. And so what I want to do is just show you when you plot shear strength measurements just individually with depth scattered across the globe, it is kind of a scatter plot. There's a lot of variability. These are all the measurements. There's 2,000 plus measurements in that plot. They're color-coded now based on whether they're from an active margin or for a passive margin. And even in the raw data, I haven't done any filtering here. You can see visually the red looks to be a little bit more enhanced on the higher shear strength axis than the blue ones, which are passive margins, meaning that the active margin sediments are for some reason stronger with depth than the passive margins. And you can see the histogram here. So yeah, there seems to be something going on with, there's a stronger signal of the sediments in active margins. There's no reason for that to be. The lithological variations, there's a lot of things that can vary shear strength, not just seismicity, but explaining this phenomenon, it's hard to explain without invoking seismicity. So in order to clean that up a little bit, we spent a lot of time trying to find locations that shared these common set of criteria, which is we wanted to look for the simplest locations. Basically, we wanted like paleoceanographic cruises that want the most pristine records. That would actually be a great one for this study. So we want places that have continuous sedimentation and burial occurring. No unroofing, no issues with erosion especially. We want hydrostatic pore pressure, no pervasive bioturbation. We want no cementation or gas hydrates. We want no evidence of past submarine landslides. And if we could find those locations, then we can do maybe a more apples to apples comparison. And thankfully, we were able to find these 8 sites that actually pretty much share those commonalities. And so the only difference then is that they're on passive margins or they're on active margins. And so when you do that and you simplify that first plot, you get this, which shows the active margins, systematically stronger with depth. And this is looking at the top 60 meters below seafloor. So this top 60 meters is important. This is the zone on our planet where submarine landslides are going to happen, if they're going to happen. And so understanding their strength properties in this zone is really, really important. So is that a significant difference in terms of slope stability? I think so. This is a factor of 2 to 3 enhanced strength above what would normally be expected. This is a normal strength profile. This matches what we would suspect from geotechnical engineering theory and years of measuring strengths with depth. This is a over-consolidated profile, the active margins, even though they're normally consolidated sediments on simple basins or simple settings. Okay, as I say, these are simple settings. Actually shows quite nicely the underlying or fundamental systematic differences in shear strengths. But it would be interesting to test these where we also have the competing or offsetting effects of high sedimentation areas. And so I wanted to go in an area that has both high sedimentation and high seismicity to see if this seismic strengthening signal actually works. So a good place to study that is here in southern Alaska, where we have the rapidly eroding coastal mountains. The St. Elias Mountains are rapidly eroding and directly connected with the marine and the offshore environment, and they are constructing a very large deep sea fan called the Surveyor fan. And IODP came in here several years ago and did a transect of cores across the slope or the shelf and down in the slope and into the fan. And I'll just show you the data here in a second, but of course this is a location where you have tremendous seismicity. The 1964 9.2 Great Alaska earthquake is there just northwest of the study area. This is a very vulnerable location to earthquakes for sure. Okay, so I just want to show you the shear strength profiles, and this is kind of interesting. Those sites that are shown in red in the Surveyor fan are plotted here. And they're just points of measurements of shear strength with depth. And so there's some scatter, but for the most part, they kind of cluster around this zone. And the thick black line is the composite of those sites. The one on the right out here is outside the Surveyor fan. Here, it's the Patton-Murray seamount chain. So it's located outside the Surveyor fan. That's significant because it's outside the fan. It's not receiving high sedimentation rates. So it's behaving like one of those active margin plots I just showed you. It should have enhanced strengthening if what we're seeing is actually happening. So it shows as a nice comparison that, okay, that site, it's not getting high sedimentation, is perhaps seismically strengthened. It's perhaps resisting quite nicely. But the fan sediments are weak. Okay, so anything in here, and especially as you get close to shore, there's no enhanced strength, and so it's weak. It's normally weak, but it's weak. And so because we have so much earthquakes, these areas are quite vulnerable, I think, to seismic shaking and submarine landslides and potential tsunamis. So that 1964 Great Alaska event triggered all of it: earthquake, tsunami, and landslides all together. And some of that may be related to the strength properties of some of these sediments that are exacerbated some of those events. If you look in the interior of the Surveyor fan, this is a paper we just published coming out of this, we see some interesting results. This is a multi-channel seismic line going through the fan. Here's one of the sites that we're just looking at. Most of that record of the fan itself is these nice layered, simple stratigraphy, relatively simple stratigraphy. And then when you get to the middle part of this line, from the green line down, we see, especially between the green and yellow, there's this very large, chaotic unit that's been identified. And we talk about it in the paper, but it's a giant slide. It's among the top 10 that we know about in terms of volume that we've been working on. We as anyone. Well, I guess we claim it's the 5th largest mapped megaslide. So this is occurring in this area where we have a lot of seismicity. So it's probably no surprise we have such a large event. But what's going on in the years since? There's been a long time since then. And it ties in the effects of glacial and tectonic interactions. At this time, which is 1 million years ago, we have a transition where we have the onset of rapid sedimentation from those coastal mountain ranges that did not exist prior to that. You had more background, slower sedimentation rates. Then about 1 million years ago, you have this start of the influx of sediment rapidly from the mountains building the fan. And so the idea that we put forward in the paper is that, okay, well, before you had the rapid sedimentation, you actually had seismically strengthened material, but you probably had enough energy. Earthquakes can overcome even seismically strengthened sediments. But when they do, that material that gets mobilized is going to be pretty thick and viscous and strong, and it's going to be a blockier style of failure than maybe something that's weaker. And so we think the fact that it's so blocky and thick is probably related to its initial properties that it had to begin with. Since then, we probably do have debris flows and turbidity currents, but they're much thinner and more fluidized because they don't have the time to develop any of the strengthening. And so they're behaving like normally weak sediments. And so they get shaken and then they get moved out to the fan very rapidly. So this is another consequence of earthquakes changing the properties of material. And it reminds me of some of the experiments I got a chance to do as a graduate student, where I was making submarine landslides in the laboratory and playing around with different compositional starting configurations and exploring differences in relatively weak starting materials to relatively strong starting materials, just based on relatively minor changes in water content and also clay or silt size, but very similar starting material. So what you're looking at is pictures, so they're oriented vertically. This is a picture of a 20 centimeter flume that's sitting inside a larger pool, and you're looking at them from the side, and it's after the landslide has occurred. And so there's a little bit of stuff left over, but most of the material, you're now looking at the front of the flume, so everything is coming out down to the floor. It's sitting on a 10-degree slope here, and then it enters out into a 0-degree pool floor there. And so there's a rapid release of sediment that gets almost, well, it does make a turbidity current, a cogenetic turbidity current, because it's so weak. And so this is the weakest type of material. This is the type of material we're probably seeing in places like, southern Alaska in the Surveyor fan when they do release. If you start with material, you keep everything the same, but you just systematically strengthen the material before you cause a landslide, you get what you expect, intuitively. You get thicker and thicker starting materials, and you get material that maybe you can still cause it to fail, but it's not going to go as far as the weaker stuff, of course. And so you get interesting behaviors, and while it's intuitive, it also gives you direct diagnostic sort of criteria to compare to real systems. So in the strongest cases, yes, you can still make a landslide, but they have very slump, cohesive blocks as opposed to full-scale remobilization as a turbidity current like you get with the weaker configurations. So we've been seeing this. I showed you the one in Alaska. I'll show you a brief one here in Oregon, just south of Alaska, that's showing the same sort of behavior in terms of the morphology of the landslide. So this is what's called the 44 north slide, just it's 44 north latitude. This is a seismic line through the blocks that you see on the map, and then up through the starting area we call the amphitheater source area. So through the blocks, you can see they stick up against the modern-day seafloor. They're significantly tall. This 100-meter scale bar here. So some of these are more than 100 meters tall, and you can see their width. They're more than 100 meters wide. So they're retaining their shape and their size as they have traversed that distance down to basically to the west, but downslope. The other thing that we notice is the blocks themselves, but also this interesting zone of deformation out in front of the blocks. We think that this is an impact-induced deformation field caused by the impact momentum of those blocks coming into the seafloor in a rapid sense. And I'll come back to that in a second. But the fact that these are blocky slides is consistent with, again, their starting strength properties. The nearest ODP site that we could find is the black one here, which is just north. Well, I shouldn't say just north, but it's north of the actual slide event there. but it's a long strike, so it's the best site we have to constrain what was the starting properties of that material, but it certainly suggests that it was pretty strong or dense when it started. And that's certainly consistent with its retaining its shape today. Okay, interestingly, yes, you can use this deformation zone, the geometry, the length, the width, to think about what it would take to do that. And if you can do that, you can constrain perhaps the velocity that that the blocks had to have had in order to make that deformation zone. So this is a fun modeling project that my student and a colleague of mine put together. And so we just asked the question, can we use this deformation to back out the velocity of the submarine landslides? And that's one of the great unknowns in submarine landslide research, is the velocity of some of these events, because we don't see them in real time, of course. Long story short, yes, this scale of deformation is consistent with blocks coming into the system at least 30 meters per second, perhaps as many as 60 meters per second. That's pretty fast, and so it's possible that this event was capable of generating a tsunami. That's another project for another day, but it shows that this event looks to be a very energetic, perhaps tsunami-genic style of event, and it's offshore Oregon. It's part of the Cascadia system, a very vulnerable area on our planet, like others that we've looked at today. So understanding how these systems are behaving and what may happen in the future is really important, and we can get at some of these things with these studies. Okay, quick time check. Am I doing okay or am I going long? I got a few more slides. Is that okay? Okay. I want to change gears a little bit here. Landslides are still going to be here. They're pesky. We can't get rid of them. They're everywhere. But I want to go to some interesting locations on our planet of hypersaline brine pools that are sitting at the bottom of the ocean in places like the Mediterranean and the Red Sea and the Gulf of Mexico. They're, I guess, somewhat common, but you need to have, salt basins, I guess, in order to feed them. And of course, you need the right conditions to contain them. But they're quite interesting for a number of reasons. They're of course extreme environments, and so they're important biologically for the ecosystems that they support. They may hold value for understanding how life persists in extreme environments, perhaps even outside of Earth. So they've been studied in a number of locations. I'm going to show you one today that has all of these elements combined. Here's a picture of a crab that is no longer living. These are deadly to some macrofauna because of the hypersaline conditions. 8 times the salinity of normal seawater in many of these locations. So they're fascinating sort of environments for that reason, and they've been studied for that reason. We've been studying one called the Orca brine pool in the Gulf of Mexico because there's a lot of evidence of potential gas hydrate underneath the walls of the basin highs. The brine itself is sitting here, so the white outline I'll just show you real quick. That's the pool, the brine pool. At its deepest, it's 200 meters thick. It's quite significant in terms of its area and volume. And one of the things that caught my attention, of course, as somebody who studies slope failures, are these blocks of sediments and failures that are at the bottom of the pool. In my head, I thought, okay, well, that's an interesting situation where we have blocks coming into almost like a bathtub, right? And it's going to slosh that brine pool and make significant disturbances and waves that then could have impacts on ecosystems around it. It could slosh brine out of the confinement of the basin. It's just an interesting sort of problem to study that could have interesting implications. So real quickly, I'm going to show you a line now, a seismic line, to look in the interior. So we'll go through this down into the interior of the brine pool next. So we start here, we're above the brine pool. This is where that landslide scarp is. So it's there, and then we go down slope, and we finally get the brine pool here. And the brine pool is this perfectly flat mirror in terms of reflection seismic, so sound waves will bounce perfectly off that. And so you can map that perfectly as a reflector, and you can calculate the thickness of the brine pool because the actual seafloor is here in the green. And then interestingly, what you see below the brine pool floor is a stacked set of MTDs. That's just mass transport deposit, just a general term for landslide deposits. And you can see the chaotic facies here. So there's a very thick carpet or bed of remobilized sediments right below where the pool is sitting. And so you can see the line interpretation here. Yeah, and so we have evidence for, there's some interactions going on with landslides. We see the blocks from the previous map and the brine pool itself. Interestingly, so you can study this in the laboratory, and people have done this. This is not work that I did, but some work here in the late 90s and 2000s that did exactly what is happening here. They basically set up a situation where you've got two fluid columns here. You've got normal water on top, and in this case it's fresh water. In this case it's salty water. But you can imagine that's very similar to these brine pool settings where you've got normal seawater versus very, very salty water. And in coming into that system, you have sediment that's coming down slope and interacting with that interface. And of course, in the perfect situation where you've got densities equivalent, in other words, the density of the sediment is equal to the density of the brine, it's going to float on the brine and hover along that interface. And that's interesting too, because it will basically flow out as long as it's capable with its energy that it came in, and then it will slowly sprinkle sediment over the floor of the basin. That's quite interesting by itself. The other possibility is what happens when your incoming density is larger than the brine density. And so this is what happens, we think, when we have landslides coming in. And it actually almost creates a little mini tsunami. It basically plows into the brine, pushes the water out of the way, and then sets up a wave that moves radially away. Okay, and so the amplitude of that wave is kind of what was interesting to me, because in fact the density contrast between the water bodies here is significant, but it's not like the air-water interface on the surface of our planet. And so it's actually perhaps capable, the amplitude of the wave anyway, can actually be larger than it can be on land. And so you can calculate the maximum wave amplitude in some of these situations based on the velocity of your incoming blocks and the density of the incoming blocks. So these are just some scenarios that we tested based on various densities and various velocities. And you can see the maximum wave amplitudes here. It's not hard to get a 100-meter wave amplitude for something that's coming into the basin at more than 10 meters per second. And that's not that fast. And if you remember the sidewalls of this Orca Basin, there's a lot of gravitational potential energy there. The sidewalls are fairly steep. So we don't really know what the landslide velocity was. That's, of course, an unknown. So it's hard to say exactly what the amplitudes are of these waves that perhaps were affecting the Orca brine pool, but this allows us to constrain some of these ideas or possibilities. One thing, of course, is an outcome of that, or a potential effect of that, again, is the sloshing effect. If you're moving that much water, you're going to bathe the boundaries of the basin walls and anything living there with this hypersaline water. And so that's a shock to anything living there that's not expecting that or can't deal with that hypersaline shock. And a lot of these brine pools, this is an example of another one, not the Orca, but another Gulf of Mexico one, that's just rimmed with a mussel bed, just sitting around the edge of that pool. So a lot of these ecosystems probably need that, of course, separation, of course, and most of the time, these are probably stable, stratified, quiescent settings, but in the right locations or wrong locations, depending on your point of view, you may not be able to always have those stable conditions because of the activity of sediments. One last thing here, you can also maybe think about losing brine out of the basin itself. And so we have to look at the spill point of the basin, which is just the lowest elevation. If water is going to escape, it's going to go out that location. And in this case, the Orca Basin, that's the spill point. And it's between the Jefferson Basin and the Orca Basin. So if water's coming out, it's going to have to go through there. Then it would enter this Jefferson Basin, and then it would go downhill. It would turn the corner and go down. So I thought about the possibility of this and went looking to see if I could find evidence of a perched brine pool because of this. And I'm not saying this is a brine pool, but it's interesting to me at least. If you do follow that potential course and you go into the Jefferson Basin and you look into this corner, there is a seismic line here that I was able to pull from years ago, and you can look at it here. There's this conspicuous really flat layer here. That could just be normal seafloor, potentially could be. Could also be the top of a thin brine pool that was perhaps caused by sloshing of brine waves from the Orca. And again, that's just a thought. They have no way to prove that. But it's interesting because when you calculate, or if you want to know the age of the brine pool, a lot of studies will focus on the volume of brine and relate that to a dissolution rate of salt. But it relies on, so that calculation can work, but it assumes that the volume of the brine in your pool has always been there. And if you're losing brine water, of course, the age of your brine is going to be compromised by these natural processes. Okay. That is just a quick survey of some of the fun projects I've been working on or am working on myself, with students, with colleagues. I give you a sense for the variety of things I do. A lot of the themes are geohazards, and we try to detect them through sedimentary deposits. I'm excited about the future. Marine science, marine geophysics, marine geology is of course rapidly expanding, as still is. Most of our planet is unmapped, as I'm sure many of you are aware of. There are some exciting discoveries that are of course out in front of all of us. So as I think about future connections and my motivation for maybe applying for things like the ICREA and other things down the road are exciting to me. And I'm thinking about Roger and his team coming back from Antarctica in a matter of days, from Antarctica, looking at hydrates and gas expulsion in that location. Thinking about this summer, I'll be here with the InSize conference that's being hosted here. That'll be a fantastic way to communicate with not only marine geologists, but others studying canyons as the focus. And there's a lot of connections with biology and oceanography and all of the staff and faculty and expertise that you all have here at the Institute. So I view this as an opportunity in the coming years for me to really enhance my own career and hopefully add some value to the things that you all are working on too. And so I'll sort of leave it there. I am happy to answer, of course, any questions you have. And then I'll just show my quick acknowledgments because, of course, there's many people and many sources of funding and students and others over the years that have supported everything that I've shown before. Okay, so thank you.
Thank you, Derek. Very enlightening
Yep.
presentation, exciting data and mapping and seismic lines.
Yeah.
So there's now time for questions. Valentin?
Okay, thank you, Derek. Very interesting. And well, I work also myself on earthquakes, but more on tomography and the structure of the interplate boundary and things like this. And I've worked in Tohoku, and I saw that you have this drilling in front of Sendai, in which you found this body. What is the origin of this body? Because it seems to be older than this Tohoku earthquake, but it doesn't appear to be any signal of the Tohoku itself, which was magnitude 9 and shake everything with a big earthquake. And it has been proposed that there were some landslides that enhanced the tsunami and this. So what's your opinion about this?
Yeah, absolutely. I think you're speaking about this event and in general?
Yes.
Yeah. Yes. In fact, I showed you a potential age limit. Yeah, so what I think what we're seeing here in this particular one is a very young event. There does seem to be some drape above the event, from here to here, to suggest it's a little bit older than perhaps the Tohoku event. There was a paper that just came out of this. Mickey Strasser is the lead PI on the project. So there is evidence for the Tohoku event in some of these megabeds in the Japan Trench. Yeah, so it is detectable. So, and I agree. I think the papers that suggested that they occurred and amplified the tsunami, I think that's correct. And I think, although it's interesting, those landslides perhaps could start on the slope. To make it out here to the basins, they have to have been fully remobilized. So it's unclear to me if there's material that's still upslope that's part of that system. And what we're seeing downslope is, of course, just the stuff that got completely remobilized. In other words, this, I wouldn't really call it a submarine landslide, it's more of a turbidite. And so that's the distinction that I think about it. We have landslides, we have turbidites. I think the landslide is probably the thing that is certainly capable of enhancing really the earthquake-generated tsunami. Anyway, so did that help answer? But yeah, please clarify.
For you, this megabed would be a single event deposited at once.
Yep.
Okay.
Yep.
Any other question? Jonas?
Thanks very much for the talk. Very interesting. I have a question related to the shear strength of the passive versus active margins.
Mm-hmm.
You measure them in situ, or you measure them in samples that you take from cores?
These are all after we've cored, brought them up, and split them open. Yeah, so they're not in situ. They are.
Okay.
They're taking on the split core.
Which is actually nice, because if they were in situ, you could argue that the higher shear strength comes from the deviatoric stresses of
True.
that appear at active margins. So
True.
So it's good that they're actually not stressed.
Well, that's a good point too, because a lot of people have asked that same question: is if you're looking at a convergent margin, perhaps you're just looking at the effects of that stress difference. And I agree with that. But I've also seen some interesting experiments in just basically dedicated triaxial experiments who've done that. And these are so shallow. That's the other thing. When you look at maybe at the margin, the scale of the margin, yes, there's certainly a convergent. There's a very different stress orientation between that and passive margins. But even on an active margin, the very shallow skin, the top tens of meters, is probably mostly being driven by the vertical.
Yeah, I would say everything would be stressed, but if you go to the next slide, you actually see the one, maybe
sorry.
it was later.
Uh-huh.
That's not very important. Where you see the trend.
Oh, this one?
No, there was a nicer one.
I think that was it. No? Those are the only ones.
It was maybe 20 slides later.
Oh,
or
actually, yeah. Sorry, you're right. This one.
Yeah, maybe. There was another one even.
Wait,
Otherwise,
let
I'll
me see
leave
if I
it.
can find it. There's another one there.
Yeah, maybe if you go one back.
Oops.
You see it actually increases. It increases early and then it remains parallel.
Yes,
Which is an other argument for what you are concluding, I think. Because otherwise it will go even steeper now. So.
Yeah, exactly.
Thanks.
Yeah, that's interesting. We actually see this. It does seem to be exacerbated in these shallowest materials, like the separation it is. And then, there seems to be some, it comes back and then they kind of go parallel. And then after that, I don't know, maybe they eventually converge. I don't know how, it's kind of interesting to think about, but because actually, if those materials are dewatered and you carry those down and they eventually get into subduction zones, it's going to affect the water budget, and it plays into how we think about volcanism and other earthquake processes at depth. Those initial sort of early burial phase processes may inherit or be inherited as they get deeper. Yeah, great. It's also a downside that we have to take these on split cores because they're not in situ. So there's pros and cons, I think. But
Thanks.
Yeah, I have another question related on this 44 North slide. Do you have any dating of the occurrences of this slide, and that could be related with all the dating of turbidites that Chris Goldfinger did on this margin?
Great question. Yes. Unfortunately, well, it's an ongoing process. There is this that dot is a piston core that was acquired, and it's in the top of the draped sediment that's sitting on top of this deformation zone. That piston core is just in a database. I have not seen it. It's in Chris Goldfinger's and his Oregon State research. So we just plotted it, and maybe someday we can go back and sample it. But at this point, there isn't a fresh age date on that. I do think in some of Goldfinger's papers, he did see, looking at maps, I think he saw this event. This seismic line is new, though. Didn't have the the value of the seismic line. But of course, you can infer a submarine landslide. So I think this is part of the mega slides that are even larger than this ones that he was postulating way back then. In the years since, yeah, there's been a lot of work actually, in not only with Chris, but the USGS scientists that are, yeah, really tying in the turbidite record, the landslide record, the earthquake record here. For obvious reasons, there's a lot of interest in constraining the timing and ages of these events in Cascadia. So, yeah, the other thing is it's a little bit of an outlier. If you look at the map here, that thing is, it sticks out like a sore thumb when you look at the map. Because if you go north and south.
Yeah, that was my next question. So do you have any other example of blocky, because this margin was a map, fully map at the time that Chris Hoffinger took the piston cores. So now you have swath bathymetry of all the entire margin. So do you have any evidence of buried blocks that is outcropping or sticking out from the basin that could see it as a target point for a seismic line to see the same deformation, same type of deformation?
Well, yes, and in fact, it's actually what we did. So Brandy Lenz here, Lenz is the author, she was a PhD student with me, and so she did this. One of her chapters was exactly what you're describing. Let's compile the existing multi-channel seismic lines up and down the margin and look for landslides and understand their number and do they vary up and down the margin, and their style. Are they blocky, are they weak? And so that's what she did. And yeah, we published this in Basin Research a few years ago. And yeah, there's actually a systematic change in the distribution of the landslides as you go north along the margin. And so, and there's also more blockier. You can find a variety of landslides, but there are certainly many other blocky landslides in the subsurface. And so, yeah, whenever, I get to pick out a nice example, but yeah, in terms of the total overall landslides here in this margin, like any margin, there's a complex, abundance of all of them, but there does seem to be more blockier landslides, and there does seem to be a spatial sort of heterogeneity here related to proximity to seismicity.
Thanks.
Yeah.
Any other question? Okay. So thank you, Derek.
Thank you.
And we hope to see you around soon.
I'll be here. Yes.
Okay.